Okay, so in this video I want to just take a look at some other surfaces that are not constant surfaces in spherical coordinates necessarily, but converting them to spherical coordinates. And it turns out some of these will end up being constant surfaces. So I start with the unit sphere, x squared plus y squared plus z squared equals 1. And that one is easy to recognize as a constant surface. That's just rho equals 1. So the equation for a sphere centered at the origin is really nice in spherical coordinates. Okay. Next, I'm looking at a half cone, and sometimes we just call it a cone, speaking a little bit more informally. Z equals root x squared plus y squared. Okay. Now, if that's a half cone, I'm thinking phi should be constant. So I'm going to find the equation two ways. First, I'm just going to do it geometrically, and then I'll actually do it algebraically. The geometric way is much, much nicer. Okay. What I'm going to do is I'm going to draw myself a picture of what I would see in a constant theta half plane. So I'm saying here's my z-axis. This would be the xy plane. So I'm viewing it as coming out like so. And I want to just look at the cross section that I have there. Now, because my half cone is going to have this rotational symmetry, I'm going to see the same cross section in any half plane. Generally speaking, I probably don't want to use spherical coordinates if I don't have a shape that has rotational symmetry like that. So if I look at my cone, it looks something like so. Okay, so we're saying that z would be the square root of x squared plus y squared. But I actually know that that in cylindrical coordinates would just be r. Okay, so here's z, that's the distance up. This distance here would be r. That's the distance to the z-axis. I can also think of it as if I projected my point down onto the xy plane, it's the distance to the origin. That's equivalent to just saying it's the distance that I get going to the z-axis. Now, this angle right here would be phi, because this is the z-axis, and this is the angle we're rotating to get this. If z is equal to r, then I know that tangent of phi is equal to 1. Okay. Well, that tells me, since phi has to be between 0 and pi, that tells me it's got to be an acute angle. Because if it's between 0 and pi over 2, tangent will be positive. Between pi over 2 and pi, tangent would be negative. So phi is just the acute angle whose tangent is 1. This is a constant surface. Phi equals pi over 4. And I think that geometric analysis of things is the nicest way to go. Let's see, though, if we can't do it algebraically as well. So we said this is equivalent to z equals r going to cylindrical coordinates here. And I want to try to get to an equation that just involves phis and r's and phis and rhos and thetas. Okay. Well, if I take a look, I know that tangent of phi was equal to r over z. Okay. So if z is equal to r, then r over z is going to be 1, except in the case where z is equal to 0. Okay. So that means r over z equals 1 unless z is equal to 0. Okay. All right. So that would mean that tangent of phi is 1, which is what we just got, which suggests that phi is equal to pi over 4. So let's just take a look. What happens if z is actually equal to 0? Well, we're actually okay in that case, because since z is equal to r, that would mean that r was also equal to 0. If r and z are both 0, that would put me at the origin. I'm not going above the xy plane, and on the xy plane I'm not going away from it. So if r equals z equals 0, we are at the origin. And if I look at the equation phi equals pi over 4, that certainly allows for us to be at the origin, because that puts no restrictions on rho. Rho's allowed to be 0. Okay. So that is my equation. I think the geometric analysis was a lot simpler. Sometimes when you are doing an algebraic analysis of things, you do need to take a look at what if these things are equal to 0. But you want to remember that just like with cylindrical coordinates, if, for example, rho is equal to 0, that puts us at the origin. Phi and theta would be free to be anything we wanted. So it's possible to have equations that are geometrically equivalent, even if they aren't algebraically equivalent. Okay, so these first two examples did end up being constant surfaces in spherical coordinates. Let's take a look at this next one, a paraboloid. That's not a constant surface. I know that. I know that because it is not a sphere, it is not a half plane, and it is not a cone, even a degenerate one. Okay. So if I wanted to convert this to spherical coordinates, I'm going to need to simply describe x, y, and z in terms of their spherical coordinates. So looking here, remember we got that cosine of phi was equal to z over rho. Okay. That means cosine of phi, that means z, is equal to rho cosine of phi. And we did confirm that that works in all cases, even if z is negative and phi is obtuse. Okay. So we're going to have rho cosine of phi equals. And then we've got x squared plus y squared. So now we've got to get x. Now with x and y, I don't go straight from rectangular to spherical until I've accidentally memorized the result. I take a detour. I say x is r cosine theta going into cylindrical coordinates. And then I use the fact from here, we can say that sine of phi was equal to r over rho. So r is just rho sine phi. So x is rho sine phi cosine theta. And then by a similar argument, y is r sine theta. So that becomes rho sine phi sine theta. So I can plug that in. So x squared is then rho squared sine squared phi cosine squared theta plus, where'd my eraser go? I'm going to just erase that result. Plus rho squared sine squared phi sine squared theta. And then I can simplify a little bit because I see the cosine squared here and the sine squared here. So I can say this is rho squared sine squared phi times cosine squared theta plus sine squared theta. And that just drops out and becomes 1. So we get rho cosine phi is equal to rho squared sine squared phi. I don't think that's particularly simpler than z equals x squared plus y squared. So if I had this paraboloid, I probably wouldn't want to switch to spherical coordinates. But it is possible to do that. And I will just point out that our paraboloid would have had this rotational symmetry about the z-axis. And anytime we have that, we should be able to eliminate the thetas from our equation. Because we are, in any half plane, we are going to get the exact same cross-section. So theta does not affect what we see if we have a surface like this that has that rotational symmetry.